gravity.
Gravity!
Gravity! Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity.
You win this one, Gravity.
From a hoop glider, to an egg drop, to a hover balloon, it's a gravity-defying dance party! All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Looks straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it to make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. We're gonna, oh yeah, I gotta clean that up. We are going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right, here I go. Aha!
Oh, hi, Phil. Good. What? Pardon? You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To replace the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa! Gravity-defying. Look at it fly! Defying. Okay, not exactly, but What if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why.
When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it.
Until there's no more tension, and then the top passes the bottom and the whole thing. That is how it works. But here is the real question.
Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring!
Let's max it out! Bring it. Don't tangle it. So now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go!
A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it.
So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa.
Sonia and I are maxing out the hoop glider out of bigger and better materials.
This is the largest tube I have, right?
A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and...
Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited.
we take our plastic and metal hoop glider outside to test it and...
Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it?
Sonia and I made a very solid design, but the problem with it became pretty obvious.
Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down. So you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. I had a big balloon and it had a, there. A giant balloon And look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Gravity. Gravity. Gravity makes things fall. But where do they fall? They fall down. Oh. Towards the center of the Earth. Eh? Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes, gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off.
Back to our hoop glider, which was too heavy.
Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
It falls to the ground. I see.
so we need something that's light
Light
and something that's strong.
and strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out.
Hoop glider dance! Okay, 3, 2, 1.
That's pretty good!
That was
Pretty
amazing!
good.
Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good!
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it.
Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I
I made this!
made a slightly heavier one.
Let's do it.
Okay, 3, 2, 1, go! Not bad. My turn.
Here we go.
Okay. Yeah. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before. to
And
see-
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome!
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
Do you
But I
we can
think
make
that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's do it. This is an egg. Eggs do not like to be dropped. Oh, So, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way, because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over, good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, Gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide. Look closely, it's the same location. Amazing. But did you know that this is caused by the gravity of the moon and the sun? See, this cookie is the Earth. And this little happy fellow is me. Hello. And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well,
That was
Pretty
amazing.
good. Here we go.
but we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot.
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great. So there you go. Giant hoop glider. Yeah, Science Max, experiments at large. Nicely done.
Nice.
What more can you ask for?
Well, my turn.
Hey, see you next time. Science Max!
This episode of Science Max is all about hot and cold. A giant hot air balloon, dry ice, the coldest temperature possible, absolute zero, and whatever this is. Blubber suit! All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. We're gonna be making one of the easiest and one of the hardest experiments to do. Here's what we're gonna make, a hot air balloon. And it's pretty easy to make. That's why it's one of the easiest experiments. All you need is a plastic bag, but not any plastic bag. The kind of plastic bags you get at the grocery store to put your fruit in. That kind of plastic is very thin, very light, good for hot air balloons. And you just want to put 2 paper clips on the bottom of the bag to hold the bottom down. Now here's the other thing you need. You need an adult and a hairdryer. Turn the hairdryer on.
Put the heat on the highest setting and the fan on the lowest setting.
The air inside the bag is getting hotter, which means the molecules are moving faster, and they're getting further apart, which means there's going to be less of them in the same space. Less molecules means less weight, and that means it's going to be lighter. The bigger the difference in temperature between the air inside the bag and the air outside the bag, the better it's going to work. So I recommend doing this outside, actually, on a cold day. When it's been long enough, turn the hairdryer off, and it will float. Haha. Now it won't float very long because the air inside the bag will quickly return to its original temperature, and it will no longer be any lighter than the air outside the bag. But it's definitely fun to fly for a while it lasts. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna max out the hot air balloon and make a giant hot air balloon. Yeah, I know what you're thinking. You're thinking, Phil, they already exist. Why don't you just get a giant hot air balloon? I mean, they're big and you... No. There's no fun in that. I want to make one I built myself. I don't think I'm going to be able to fly in it, but it'll still be pretty cool, I bet. I just need someone to help me. Oh, I know. Michaela from the Ontario Science Center. Hopefully she's not busy.
Oh, hey, Phil. How's it going?
Hey, Michaela, how are you?
Good, how are you?
Good. I was wondering if I could get your help with an experiment. Do you have some time?
Yeah, I'd love to help out.
Awesome.
Sure.
Okay, let's go back to Science Max headquarters and I'll show you what we're gonna do. Okay,
Nice.
so ready? Here we go.
Oh, no, still here. Still here.
Why are we still here? That's weird. Okay, I know. No? Why is the code not working?
I think that's the Science Center code. Try the
Oh, it's the lab code. Right.
Phil, are you okay?
Yeah.
Are you okay?
Yeah, no, I'm fine. So, Michaela, I'm glad you're here because today I want to max this out. This is my hot air balloon. It was better before, I smushed it in my pocket. But what I did is I used a hairdryer, and then I put it in and I heated the air, and then it rises up. So in order to max it out, pretty simple. I just get larger bags, right? And then I thought we could cut them and tape them together to make a much larger balloon.
It's a good idea, but you know, if we're making a hot air balloon, we need to make sure our materials are really light. The duct tape seems a little heavy. Even this bag seems a little heavy to me.
In terms of, oh, you mean
terms of
the
weight.
kind of plastic it is might be a little bit.
It seems really thick, this one.
Well, do you know for sure?
I've never tried it before.
All right, well, that's science. We should try it and see what happens.
Let's try it.
Okay, so I'll cut along the side of the bag. You see that? Carbon dioxide gas. Our bodies breathe in oxygen and breathe out carbon dioxide. Did you see it? Oh, take another look. How about now? No, you didn't see it, right? Because carbon dioxide is invisible unless you freeze it. This is dry ice, frozen carbon dioxide. And this is wet ice. It's not really called wet ice. It's frozen water. Now, you know what temperature water freezes at? Starts with a 0, ends with a, well, it's actually 0 degrees Celsius. And this freezes at -79 degrees Celsius. It's much colder. I have to hold onto it with a glove because if I held onto it with my bare hands, I'd get frostbite. So here's the experiment. If I pour some liquid water on the dry ice, will it freeze again? Let's find out.
Because the dry ice is so much colder than the freezing point of the water begins to freeze from the bottom up in room temperature air right before our eyes.
Whoa! Totally frozen! Cool! Cool.
In order to build our hot air balloon, Michaela and I are taking clear garbage bags, cutting them along the seams so they end up as one thin sheet of plastic, and taping them all together with duct tape into a balloon.
Okay, so that's how many
Nice.
bags is that?
It's like 12 bags.
Well, so you think that's big enough?
I think so. It's pretty big.
Okay, I think we can stop there. Okay, so where's the opening again?
I think it's on your side.
Hope you didn't duct tape it close. Okay, no, we're good. We're good. So it's going to inflate like this. Wait a minute. Let's make sure it works. Is it working?
Kind of.
I don't know if it's inflating. Okay, good. So it does inflate. It does hold air,
Yeah.
right? So should we try it?
Yeah, let's try it.
Okay, so we're gonna use a hairdryer, right? And now we wait. It's working.
Kind
Right?
of.
Oh, yeah.
Woohoo.
Okay, it's almost inflated.
All right.
Okay, what do you think?
Yeah, let's try it.
Okay, on the count of 3, we'll throw it, okay?
Okay.
All right. 1, 2, 3. It didn't quite,
Not quite.
Doesn't-
Aw.
doesn't quite float,
It's
huh?
still too heavy, Phil. I think we got a couple problems here. The duct tape is really heavy.
Yep.
Also, these bags themselves are really heavy.
Okay, well, if we want to fix the duct tape problem, we could use lighter tape. Like, what if, we use invisible tape, or as I like to call it, science tape.
Science tape.
Which would be lighter than duct tape.
That's a good plan.
But what do we do about the bags?
Have you ever seen those, you know, those dry cleaning bags?
Oh, wait, I've got one. I've got one here.
Cool. Perfect.
Aha!
Yeah,
Because,
perfect.
you know, when I get my lab coats dry cleaned, so let me see here. Oh, yeah, this is much lighter. This is kind of the same material as the grocery store fruit bags, right?
I have a better feeling about this one.
So lighter tape, lighter bag means a much lighter balloon. Okay, well, let's try it. First, I should probably take my lab coat out. This is water. Now, it's ice water. Science! Okay, no, that's not the science part. Here's something you can do at home. Get some ice water and a way to time yourself and stick your hand in the ice water. it's a little hard to stick your hand in ice water for a long period of time because after a while, it starts to hurt. But don't worry, the pain that you're feeling isn't actually because you're damaging anything. It's just your body's way to tell you that you need to take your hand out of the cold water. Yeah, you usually can't do it for very long. But some animals, like seals and whales, they live in ice water all the time. They live in the Arctic, so how do they do it? One word, blubber. Blubber is a layer of fat that protects you from the cold, or protects a seal and a whale. We don't have blubber, but we are today gonna have some blubber because we're gonna make a blubber glove. Blubber glove, I love saying that. Here's how we do it. First, we want blubber. Okay, this isn't blubber, this is lard, which is actually animal fat. You can use lard, you can use margarine or butter or shortening, anything with a lot of fat in it. And remember, this is messy, so definitely get an adult to help you. So we've got our lard, and we need a bag. So what you're gonna do is you're gonna take a scoopful of lard, like this. And you're gonna put it in the bag, like so. Like that. There we go. And then you're gonna start smoothing out the blubber or the lard like this. Because what you wanna do is have a nice thin layer all the way around. See? Starting to work? Yeah. Then seal the bag and tape the edges. A square of blubber. Then do it again. Here I have 2 bags of blubber, and I've taped all the way around the outside. So I have a blubber glove. Check it out. So let's try it out. I stick the blubber glove in the ice water. It's completely working. It is not even cold. The blubber is completely protecting my hand from the ice water. I'm not even remotely cold at all. That is very fun. So, try it yourself. A blubber glove. Now, how do we max out a blubber glove? Watch. Water, ice water. I know for a fact that I wouldn't last more than 10 seconds in here without my blubber suit. I'm gonna make an entire outfit of blubber. I've got them in large plastic bags, and I'm going to get completely suited up in blubber with the help of Trevor and Stephanie. Okay, guys, suit me up. It's very heavy. Let's just go like this. Oh, okay. Time to cut back on the cookies. All right, let's do it. All right. Blubber suit, go! I can't. Okay. Okay, here we go. In. Okay, so far. Oh. The legs are warm. And. Oh! Blubber suit! Ha ha ha! I am a seal! Actually, here I am in the ice, and I don't feel too bad. Blubber suit works! Ah! Blubber suit's refreshing, actually. You just sit back and chill out. Well, there you go. Blubber suit success. Seals and whales are able to stay in ice water for their whole lives because they have protective layers of blubber, just like I do. Okay, so now, all I have to do is get out. Blubber suit! Oh no! My blubber is leaking! I've sprung a leak! My blubber! Oh, my precious blubber! No! What a world! Oh, hey, how you doing? Shut the door, it's cold out there. Cold enough for you, huh? Well, that's nothing. Let me tell you. You know what temperature water freezes at? Yeah, 0 degrees Celsius. But even that is nothing. Let's say it's winter in Winnipeg. It can get down to -20, maybe even -40. But even that's nothing. Liquid nitrogen, -196 degrees Celsius.
But even that's nothing. The vacuum of space! Minus 271 degrees Celsius. But even that's nothing! So, what's the coldest temperature? What's the coldest temperature you can have? It's called absolute zero, minus 273.15 degrees Celsius. At that temperature, all the little wiggling that particles do comes to a stop. Everything is frozen. No more movement, no more energy. Everything stops. It doesn't get any colder than that. Absolute zero is the ultimate nothing. Brr, time to get your mittens on.
Our first hot air balloon didn't float very well.
It's still too heavy, Phil. I think we got a couple problems here.
So we're making a lighter version out of dry cleaning bags and science tape, both lighter materials than our last version. We also went for more of a square shape than our last version, which kind of looked like a sock. Once we were done assembling, we got the hairdryer and tried it again. Ooh, it's sort of working.
Kinda.
It's inflating. That's something.
Yeah. It's a start.
It feels warm, like the hairdryer is actually making a lot of warm air in there.
Yeah.
This is definitely working better than the last version because it's so much lighter.
Yeah.
Wait a minute. Almost got it.
Oh,
Yeah, it's sort of working, right?
cool. Kind of.
Okay. Ready?
Are we testing it?
Turning off the hairdryer. Huh. It kind of collapses the moment we turn off the hairdryer.
Not what we expected, was it?
Yeah.
No.
I mean, it sort of works.
The thing is, our balloon is so big that we need to heat up all of the air that's in there. I don't know if this hairdryer is strong enough.
I think you might be right. So we just need something else that pushes heat.
Yeah, more heat.
So
More power.
like a heater of some sort. You know, we've got some heaters up in this room, actually, and maybe I could just tear one out. We can use that.
I like it.
Okay.
Let's do it. All right.
There.
Got it.
An industrial heater. And this is going to work just the same as our hairdryer. It's going to blow a lot of hot air up here, but this is way more effective than a hairdryer, right?
Yeah, way more powerful.
So we put the balloon over here, hot air comes up, the balloon inflates, and hopefully flies.
Hopefully.
All right, let's get the balloon. So we put the balloon on the heater and turned it on. But it doesn't seem like much is happening. That's because the heater pushes less air, but the air is much hotter, which means it took longer. Should we have brought a book? But soon it was inflating.
Definitely a better result than the hairdryer.
Okay, you ready? I think it's gonna work.
It's gonna be awesome.
All right.
Yep.
1, 2, 3, let go.
Lift off.
Yeah! It's like a giant jellyfish!
That's huge.
Uh-oh, it's tilting, it's tilting. No, no! Oh no, it's going back down. Okay, so the balloon flies, which is great.
Awesome.
The problem is it turns over in the air.
Yeah, I noticed that.
And if it turns upside down, then all the hot air comes out and it doesn't fly anymore.
I was thinking next time if we make it bigger, what if we had a little weight at the bottom just to keep it stable?
Oh yeah, okay, I've seen balloons that have sort of an X, like a very light wood that goes across the opening at the bottom.
Oh.
Maybe we could tie a piece of rope to that to keep it weighted. And if the bottom is heavier, then it won't flip over upside down, right?
Love that idea.
So we're gonna weight it at the bottom with a little X so that it doesn't flip over. And we're gonna make a bigger balloon.
We're gonna need more bags.
Oh, right, back to the bag store.
Thanks, sir.
Okay.
Wait for me.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Strange. The spoon is no sharper than it was before. Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker, and today we're cooking with coal. Today we're going to learn how to make a drink cool. Look at this bottle of lemonade. It's warm right now and not very refreshing. So what's the best way to cool this down? We put it in ice, right? But did you know there's an even better recipe than ice? You can make ice colder. It's true. All you need to do is add salt. I've got a second bowl of ice and a second jug of lemonade, and I've got 2 digital thermometers. What I'm going to do is add salt to this bowl. What the salt does is starts to melt the ice, and that actually consumes heat. This is called an endothermic reaction, and it absorbs heat, which makes the ice colder. And as you can see, this bowl of ice still sitting at around 0 degrees Celsius, but this bowl, -8 and falling. Wow. So there you have it, making something even colder than ice would normally make it. That is a way to make a refreshing glass of lemonade. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
With our new heater and lighter materials, our hot air balloon was floating free. That is, until it tipped over. When that happens, all the hot air inside escapes. But Michaela and I have a solution. So we decided to build an even bigger hot air balloon and add a way to keep it upright.
So the process, aside from that, is pretty much the same. We put the end over top of our industrial heater, and I will plug it in.
Get that hair dryer again for good measure.
It's working, it's inflating, but we gotta keep fluffing it up, otherwise it just sort of sags. But you can see the top of the balloon is definitely working. It's a lot bigger than the last one, though. Do you think we made it too big, Michaela?
It's really big. I think it's working.
It's definitely working. Uh-oh, pull your side.
Oh, man.
Oh, it's totally working. I'm so surprised that this works so well. So the stick is gonna keep it balanced so the bottom faces down, but Michaela's gonna tie a string to the stick so that when it goes up, we can keep it centered. Okay, this looks good. You wanna let it go?
Yeah, are we ready?
Okay.
Okay, 3, 2, 1.
Whoa!
Yeah! So let's recap. The hotter air inside the balloon is less dense than the colder air on the outside. And because we were able to get the air hot enough and the balloon light enough, it floats.
Science Max, experiments at large.
Hot air balloon.
Thank you, Michaela. That
Awesome,
was...
so cool.
Wait a minute, who has the string?
Oh, no.
Oh no, oh no, oh no!
Science Max! Today we're moving air. We're moving it through a tube to make a Stomp rocket, vacuuming it out, turning it into a vortex, and taking it with us underwater. All on this episode of Science Max Experiments at Large.
That was amazing! Greetings, Science Maximites. My name is Phil, and it's moving day today on Science Max Experiments at Large. Let's see, where do I put this? This is probably a good spot. Today, we are moving air. You probably don't think that moving air will have a huge effect, but you'd be surprised what you can do by just moving air. But don't worry, we're not just gonna move the air around in boxes. We are going to build a rocket! And this rocket uses the science of stomping on something with your foot. This is a Stomp rocket, and it works by stomping on this plastic bottle, and air shoots through this tube and pushes the rocket up into the sky. And here is how you can build one of your very own. And remember, if I go too fast, don't worry, all of the steps are on the website, so you can follow along at your own speed. All you need is a 2-liter plastic bottle, 3 kinds of tape: electrical tape, duct tape, and science tape. Science tape is just the same as invisible tape, but I use this kind of tape for science. Then you want some plumber's tubing and some construction paper to make your actual rocket. First, you want to take your plumber's tubing and cut it into 3 lengths.
And when I say you, I mean an adult, because you need to use a saw. So you saw it up into a long piece, a short piece, and an elbow piece.
We want to make a long tube at the top, and then we also want to make a tube at the bottom so we can attach our 2-liter bottle to. And there we go. Ta-da! Ready to go. But of course, it doesn't stay up, so we have to attach it to a base. And it will look like this. And you see, it's been attached with duct tape here, and I've used electrical tape, and I've wrapped that part around there. Now, building the rocket.
Wrap the paper around the tube and tape it with your science tape. Tape the top closed so no air escapes. Then cut a semicircle to make the nose cone and 3 hoops for thrusters and tape them to the bottom.
There you go. The rocket fits on the tube just like that. And when you stomp on this bottle, it launches. But here's the most important part. The one most important rule of launching rockets. You shoot rockets outside. Come on. Once you get outside to a nice open area and you bring your safety glasses with you, all you need to do to make the Stomp rocket work is, of course, stomp on it. You ready? Here we go. 3, 2, 1. Whoa! You see that? That was amazing. Okay, so this is where we're gonna start with the Stomp rocket. I'm gonna meet Chris from Logix Academy, and he's gonna help me max it out. In fact, he's probably at Science Max headquarters already. I should get over there. Okay, where's the... Oh, there it is. Okay.
How you doing?
It's good to see you.
You too.
Chris is from Logix Academy, and you guys do in-class robotics workshops, right?
That's right, we do.
Great. Well, I was hoping I could get your expertise to help me max out the Stomp rocket.
Yeah, Logix makes one of these. I totally think I can help you with that.
Fantastic. So it works great. I just want to make it bigger, better, more maxed out.
First off, we can start by making this pipe a little bit bigger. So larger pipe, more airflow, bigger launch.
Okay, let's do it. Cool. Moving air isn't that hard, right? I mean, air is super light. How hard can it be to move? Well, here's an experiment you can do that lets you measure how hard it is to move air. So what I'm gonna do is I'm gonna hit the ruler with the broom. It's gonna go over there. I hit it, and it moved, no problem. So we're gonna do it again. Except I'm gonna add just a couple pieces of newspaper. All right, ready? Aha, the ruler broke because this time I wasn't just moving the ruler, I wasn't just moving the ruler and the newspaper, I had to move the ruler, the newspaper, and all of the air that was on top of the newspaper. And that resistance was enough to break the ruler. Pretty good experiment, right? Let's max it out. I've got more table space, I've got a piece of lumber, and instead of a newspaper, I have a tarp. Now the tarp is very light. It is not the weight of the tarp that is going to be the difference. It is how much air I need to move when I hit this piece of lumber. And I've got a Science Max hammer. So first of all, you're not gonna try this at home, right? Deal? Okay, deal. No trying this at home. Okay, here we go. Moving air, test 2.0. It broke, and it didn't even move. Did you see that? I wonder if we can max this out even more. 2x4, which is much bigger than the piece of wood we used last time, and a sledgehammer. Here we go, moving air experiment 3.0. Wow! Yeah, science. Whoa.
So I've joined Chris from Logix Academy, and we are maxing out our Stomp rocket. To do that, we're gonna use...
Larger pipe, more airflow, bigger launch.
The theory is that moving a larger volume of air through wider pipes will make our rocket work even better. So we get to work. This version is built exactly the same. We cut and attach the pipes, a long piece, an elbow, and a short piece, then secure them all down. We attach the plastic water bottle and tape it so it's airtight. And then the only thing to do is make a new rocket that fits over the larger pipe.
Ready to try it?
I'm ready to try it.
All right, let's do it.
Let's go.
1, 2, 3, go! That was amazing! amazing!
In the end, though it worked, it wasn't much better than the smaller rocket.
I think we could still do better, right?
Oh, yeah.
This is Science Max, not Science Medium. Right, okay, let's go back to Science Max headquarters. Vacuum sealing. That's what you call it when you take all of the air out of something, often a bag, to seal in the freshness of food. I will demonstrate using this Science Max banana. 100% banana, but with added science.
Not all bananas contain science.
Here's how you can do it at home. Put your food in a bag, seal it most of the way, because we have to take out the air from the bag. And we will do that with a straw. Put a straw inside the bag, and then suck the air out of the bag, and then seal it at the very last second. There, a vacuum sealed banana. Now I know it's kind of hard to see that it's been vacuum sealed because bananas don't really crush much when you take the air out. So I like to use stuff that has a lot of air in it to begin with. In fact, there are special bags that are specifically for vacuum sealing that are supposed to store big and bulky items that have a lot of air in them, like this pillow. See this nozzle right here? It's designed to be used with a vacuum. Haha. So, what you do is you put the vacuum on this nozzle, open it up, and then you turn the vacuum on.
Oh. The vacuum is sucking all the air out of the bag, just like we did with the banana. But because the pillow is full of air as well, it starts to shrink and shrink.
Then you pull off the vacuum and you tie the seal off, and, all right. And ta-da! A vacuum sealed pillow. Okay, let's max it out.
What could possibly be more maxed out than a vacuum sealed pillow?
Vacuum sealed fill. Okay, I put plastic bags against the door and then sealed the edges with duct tape. And of course, I didn't put any plastic over my head because you never put your head in a plastic bag, right? Well, let's see if vacuum sealed fill, it works. Whoa. Hey, it's working! Ha-ha!
The vacuum sucks all the air from the bag, which seals the bag and me in it to the wall. That means
I should be able to knock this milk crate out from under me.
air pressure, or the lack of air pressure, is keeping me sealed to the door.
I'm completely suspended! Uh-oh. I shouldn't have done that. No.
So our larger version of the Stomp rocket worked, but it didn't go as high as the first version. Chris and I see how we can improve the design.
The larger pipe and the larger rocket works really well.
It does work really well. I am afraid, though, that the larger pipe means that the same amount of air is flowing slower out the nozzle than it did before.
Oh, so because we're moving only this much air, it's not going to go as fast because this is a bigger tube.
We need a bigger volume over here to match our larger
So a
nozzle.
bigger bottle.
That's right.
I got a bigger bottle right here. Ha-ha! Bigger bottle! So hold that, and then all we have to do is tape the bigger bottle
I'm not sure
on.
if that's gonna...
Yeah, like this.
Still, though, I'm crazy.
Yeah, so then all I need to do is tape it on.
Chris and I attach a larger bottle to our tube. We just need some risers to adjust the height, then we tape it on and we're good to go. Everything else, including the rocket, stays the same.
I still don't understand how you're gonna step on this one. It's just too stiff.
I have a plan. Ha 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 ha! Sledgehammer! You ready?
Yeah, I'm ready.
Okay. 1, 2, 3! It blew the top off the rocket.
Right off
It
the
also
top.
blew the bottom.
Looks like it's a bit rigid to change its volume so quickly.
So it's kind of a one-time use thing, huh?
I think so.
So why don't we try increasing the volume? Even bigger tube,
Yeah.
even bigger container.
What's bigger than a... That's the biggest bottle they make.
What else holds air?
What about an air mattress?
Do you think we could use an air mattress?
I think we could, yeah. A really big air mattress.
Oh, totally. High five. I love that idea. Living air is a lot of fun, especially if you use one of these, a Vortex cannon. They're pretty impressive and they use some pretty amazing science. I'll show you how to build one. It's pretty simple. All you need is a plastic cup, you want a balloon, something round, an elastic, scissors or a craft knife, and a pen. Here's what you do. Take your balloon and cut it just where it gets wide. You take the mouth of the cup right there, and you have to stretch the balloon over the top. And then you want to put an elastic around it, keep it in place. And this now is a surface on the top, and that's what you're going to use to pull back and create your burst of air. But of course, the air's not going to go anywhere until you make a hole in the bottom. So here's what you do. You take your round thing and draw a circle, and take your craft knife or scissors and an adult and get them to help you cut out a hole. And when you pull back on the balloon, a burst of air comes through the hole. But the air has an interesting shape. Now, I know what you're thinking. You're thinking, Phil, air is invisible. You can't tell what shape it is. Well, I can show you. Come on. This is my maxed out Vortex cannon. It's made out of a garbage can. I've got a hole in here, and this is a shower curtain with a ball that I can get a grip on and pull. And then it shoots forward like this. Now, it makes a big puff of air, but again, the air is invisible, so we don't know what shape it is. But I can help with that because I've got this, a fog machine. I fill the inside of the garbage can so we can see what the air is doing when I fire the Vortex cannon. Okay, come on over here. Ready? Whoa! Okay, ready? Check it out.
The Vortex cannon shapes the air into a ring, called a vortex.
It makes a ring. Well, actually sort of a donut.
Because of its shape, the air in a vortex can move much farther than air that doesn't have a shape.
Vortex cannon. Air that has a shape goes a lot further than air that doesn't have a shape. And it's also way more fun. Woohoo! Little to the left. Little to the left, Ramona. Okay, now that's too far left. I don't know what you think. Oh, hey, I don't suppose you're going on vacation anytime soon. Well, if you haven't decided where, may I suggest underwater. But don't forget to pack the most important thing when you go. Hat? Nah. Ukulele? Nah, forget about it. Rubber chicken? No. Sunscreen? Forget about it. Teddy? No, if you're going underwater, the most important thing you gotta pack is air. You see, human beings have been coming up with ways to go underwater for a long time, but the thing is, you gotta bring air with you because, you know, breathing is good. Check this out. It's a diving bell. One of the first ways humans used to be able to take air with them when they went underwater. You see, it's a big, heavy bell, and it's lowered from a ship above on a rope. And when it gets lowered into the water, it traps a bubble of air underneath. So you can swim around underwater, but then when you need to breathe again, you don't have to go all the way back up. You just pop under the bell and take another breath. Bells like this were actually much bigger when they used to use them for diving to hold more air. Huh? Ring-a-ding-ding. What do you think? You want this? No? It's okay. I got something else. Hold on. Check this out. It's an old-timey diving suit. Air is pumped in through these hoses here, which means the diver has a constant supply of air, which means he can stay underwater longer. What do you think? No? Okay, hold on. I got something else. Yeah. This is it. The ultimate in bringing air with you. The scuba suit. This tank holds compressed air, which means it can carry a lot of air with you, which means you can stay underwater for longer. So I'll tell you what, I'll wrap up all three things. What do you say? Yeah? You'll take them? Okay, great. Let me just wrap them up for you. Come on, Teddy, let's go find the bag.
So our large Stomp rocket hasn't worked perfectly. A small bottle didn't move enough air, but our larger bottle was too rigid to stomp. And when I used a sledgehammer, it was so sudden the bottle broke and also blew apart the rocket. Chris and I need a large container of air that is soft enough to change its shape easily. So here's the current plan. An even larger pipe, an even larger rocket, and we use an air mattress. We make 2 holes in the air mattress, one to fill it up with a leaf blower, and the other hole to go out the tube to the rocket. Since an air mattress holds lots of air and is very easy to change the shape by jumping on it, we figure it'll be a great way to get lots of air through the tube to launch our rocket.
Okay, let's do it.
Let's do it.
All right, we're gonna go 1, 2, 3, jump, right?
Okay, yeah.
1, 2, 3.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello! Welcome to Cooking with Science. I'm Buster Beaker. Whenever friends come over, I like to make my famous potato chip recipe. And look at this bag of potato chips. Quite large, there must be a lot of potato chips in here, right? Well, let's open it. What? This potato chip bag is mostly air. Why do potato chip bags have so much air? Well, to tell you the answer to that, I have to tell you the story of 2 bags of potato chips. Here they are. This one full of air, and this bag of potato chips, there's not much air in it at all. Why don't they make them like this? Well, let's find out. First thing that happens is the potato chip bags come off the conveyor belt at the potato chip factory where they get packed into a crate. Here's a crate here. So let's really stuff them in. And then the crate gets boxed up and shipped off to the store. Oh, it's a bumpy ride to the store today. Now we're at the store, and then you come along. Bags of potato chips. What else should I buy today? Oh, I know. How about a cantaloupe? Very nice. Some apples, yes? And take it home, walk along, and you get to the kitchen, you have a choice. This bag of potato chips, where all the potato chips are light and fluffy, or this bag of potato chips, which is not exciting at all. And that's why potato chip bags have so much air, to protect the potato chips from getting crushed. Speaking of potato chips, time to get back to my recipe. What is it? It's potato chip soup. Well, I'm Buster Beaker, and thanks for joining me on Cooking with Science. Perhaps a little bit more cooking.
Okay, so where were we? Oh, right, our maxed out rocket. A much larger pipe, a large air mattress, and the largest rocket yet. Let's see how it goes.
1, 2, 3, jump. 1, 2, 3. Whoa! Yeah! There he goes. All right, let's do it again.
Okay.
1, 2, 3.
It works amazingly well. The large volume of air Chris and I can move by both jumping on the air mattress gets transferred through the large pipe, and even though it's a giant rocket, it sails higher than any other version.
That was great. That was amazing.
All right.
There you go. Science Max, experiments at large, moving a lot of air.
That has to be the biggest stomp rocket ever.
Biggest stomp rocket ever. Let's do it again.
Okay.
Okay. Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large.